My name's Gordon Lindsay and I'm an engineer with Broadcom. And today we're going to show you how we turn sand into fun. We make microchips, but not this kind of microchip. If you've got any of these gadgets, you'll be surprised to learn that in fact there's Broadcom chips inside every single one of them. Everything we make is for communications, for different ways of connecting machines together or for people to communicate. So where do we begin to make these microchips? Well, we start with sand, and there's lots of sand available. It's not going to run out anytime soon. We take the sand and it's refined into silica, which is usually used for making glass. But if it's refined further, we can make single crystals of silicon out of it. And these crystals, as in the picture, are about 2 meters long and 30 centimeters across. And then we take that crystal and we slice it up into wafers. Now, just to make this base material requires chemists, metallurgists, material scientists, crystallographers, and many other engineers and scientists. So how do we make anything with it? Well, we use a device called a transistor. The transistor was invented back in 1947 by William Shockley. And this is a picture of his first experiment. It's about 30 centimeters high and sits in the Smithsonian Museum now. So a transistor was invented about 65 years ago and it evolved into the integrated circuit a decade later. So what is a transistor? Well, it's like your bathroom taps. It's a control device, an amplifier, and a switch. And you can turn it on slightly and get just a few droplets of water, or you can turn it on full and get gushing water to come out. Only a transistor does this with electricity rather than water. But a transistor can do much more than just on and off. It could do left and right, or hot and cold, stop and go, light and dark, up and down, or open and close. And things get much more interesting when you connect more transistors together and make complex circuits and functions. However, wires and connectors are unreliable. So imagine if your tablet looked like this with lots of wires and connectors on the back. It wouldn't last for very long. So in 1958, Jack Kilby invented the integrated circuit, which had at that time just 2 transistors. And in 1971, Intel introduced the first microprocessor. That had 2,300 transistors. What Jack Kilby invented was a process much like this layered cake, in that you could build up transistors in vertical layers by stacking the layers on top of each other, just like the cake. With this integration, it produces a lower system cost, higher reliability, and better quality of devices. Now, to make multiple devices is a bit like using a potato stamp. We take one design and we copy it many, many times onto the silicon wafer. And this has got thousands of copies of the same design stamped out repeatedly across its surface. And when they're all finished, a very sharp saw is used to cut each individual circuit out and then package it so that it can go into the gadgets that you use today. A man called Gordon Moore noticed that as the technology developed, the density of transistors in the circuit literally doubled almost every 2 years. Here is a wireless LAN card for a PC from about 4 years ago. And this is a wireless LAN card from a PC today. And you can see it's about a quarter of the size in just 4 years. Over the years, this rule known as Moore's law has been proven to be quite accurate. When Intel made the microprocessor, it had 2,000 transistors, where today Broadcom makes circuits with 4 billion transistors on board. That's a 1 million times improvement compared with the early technology. And the reason that we make chips smaller and are constantly trying to shrink them down is that we can then get more features per square millimeter and more functions on each chip. We can get a lower cost per device, we can get lower power and longer battery life, and we can get higher reliability by building complex systems on a chip. And we can also get higher speeds. Intel's microprocessor ran at 100 kilohertz, and now we can reach speeds of 100 gigahertz. So making complex circuits allows us to do things like this. This is a Raspberry Pi microcomputer, which you might use at school or at home. It's a whole computer on a single chip, including the graphics and sound, and you can plug it directly into your television, and then add a keyboard and a mouse, and you can start writing programs or playing games. So today's volume production is done in what we call 40 nanometers. That's the width of the transistor. That's 0.00004 millimeters. And we can show the relative size of this transistor compared to some other things using some assistance and a tape measure. This matchstick is going to be our transistor. This is 1 millimeter across. So if you compare the transistor with a piece of normal dust, that would be about 500 times bigger than our transistor, which is about 50 centimeters. And then something you're all used to, which is the thickness of a human hair. Well, a human hair would be 2,500 times bigger than the transistor. So this is the relative size from here to that matchstick of a human hair to our transistor. Now, to make something that small means that the production factory has to be very, very clean. And it means people have to wear these nice suits when they're working in such a factory. Now, the people in the picture are also wearing face masks. And the reason for that is that you're not allowed to sneeze, because viruses are between 10 and 300 nanometers. So some particles are smaller than the transistor, but some are also bigger. So if you have a cold, you get sent home. And the devices we build are typically systems on chip. And I can use the example of a mobile phone. You may remember simple mobile phones, which only had a cellular baseband, power management, and a Bluetooth and FM radio in. Compared with the smartphones we use today, which include applications processors, GPS and sat-nav, Wi-Fi, and mobile television, there's been a big change in the last 10 years as we've been able to make more and more complex devices. So the next time you have any of these gadgets, just think about what actually goes into them and how many engineers and scientists were involved. I hope that's given you an overview of how we can turn sand into fun and make microchips at Broadcom.